Okay, good morning, good afternoon, and good evening, everybody. I'm Yi Cui. I'm a professor of material science at Stanford University. I also serve as the executive editor for Nano Letters. It's my great honor to welcome you back to our fourth event of Nanoscience Global Lecture. Well, this year is not an easy year. This will be the last event of our symposium of this year. So next year we'll start a new one, certainly. We have three outstanding speakers joining us in this event to celebrate the holidays and to open up a new chapter next year. Hopefully pandemic next year will pass. In this special event, we have, it's absolutely a great honor, two amazing editors and Nanoletters, Terry Oldham, and ACS Nano, Paul Weiss, to join us, as well as our Nanoletter early career board member, Excitonic Nack, to join us to celebrate this, the end of the year. I will introduce individual one right before their talk. Let's start with Professor Paul Weiss. Let me introduce Paul while he's sharing his screen and putting up the slides. Paul is so well known now, certainly a long time ago already well known. And everybody working in nanoscience will know Paul. He's a professor, the UC Presidential Chair and Distinguished Professor of Chemistry and Biochemistry and Material Science Engineering at University of California, Los Angeles. Paul, of course, have achieved a lot of, research, and he has done great service to the whole community. For the time consideration, let me only highlight a few points right here. He's the founder and editor-in-chief of ACS Nano, a highly successful journal. He has won numerous awards. Let me just mention only two honors. He's a member of American Academy of Arts and Sciences. He's a foreign fellow of the Canadian Academy of Engineering. And with that, let me pass the podium to Paul.
Well, thank you so much for this invitation and the opportunity to share our work. As many of you know, ACS Nano came from Nanoletters. Paul Albasados and others at ACS suggested that we should exist. And back in 2007, we started with both Paul and Terry Oldham on our editorial advisory board and as authors and advisors from the very beginning. So we really appreciate this opportunity to connect and to reconnect between ACS Nano and Nanoletters. So what I thought I would do today is talk about a problem that we thought we would be addressing in about a decade, but actually because of a comment that was sent in on one of our papers. See, there's a journal aspect to this talk as well. Because of a comment, we were jumped forward and able to get started on this much earlier than we had earlier anticipated. And so the idea is that contacts are simultaneously chemical, physical, and electronic, and that there's no reason we shouldn't be able to use a combination of chemistry, material science, and nanoscience to optimize them. And when I say optimize them, I mean make them atomically precise so that their properties, so that transport across those contacts are either perfect or as perfect as can be. And I'll show you examples of how we're trying to do that. And the latest spin, if you will, on this topic is that we'd also like to control spin at the interface. And I'll talk about chirality at the, and where we're trying to go there towards the end of the talk. Oh, I got ahead of myself there. There we go. So one of the things that happened after a decade of the National Nanotechnology Initiative was that the White House Office of Science Technology Policy asked us to say what it is we'd learned with over $1 billion a year in funding and what we might do if there was a second decade of such funding. And that seemed like an important question to answer. And so as editors and advisors, we got together and we realized that there were really two things. One is we're able to make atomically precise structures, and that's the subject of today's talk. But the other is that even in those precise structures, there's a tremendous heterogeneity at the functional scale. That's important too, but that's not today's talk. We also realized that the advances in biotechnology really came from targeting problems and developing new tools, and that nanoscience and nanotechnology could and should do the same thing. And then finally, that there was something that we had in nanoscience that other fields did not, to our surprise, and that is the ability to communicate fluently across disciplines. And that's what we train our students and postdocs and junior colleagues and each other to do because of the development of the field. And for whatever reason, that hasn't happened in other fields. And so I'll refer you to these pieces where we discuss those ideas in greater detail. And today we'll target perfection, and that's appropriate given that Terry Odom is here giving the next talk. So once upon a time in the early days of nanoscience and the invention of the STM, we realized really that we had more than a structural tool. And back then, when I was at IBM, I was the first one to be able to move atoms around. It was before my mentor, Don Eigler, learned how to spell and later made this quantum corral and a number of other famous images. In addition, to me, the most important STM image ever recorded was this one out of the IBM Yorktown labs with Joe Strosio and Randy Feenstra, showing that they could measure both the empty and the filled orbitals on a surface. In this case, the stoichiometric gallium arsenide 110 surface, where because, sorry, I teach freshman chemistry, gallium is less electronegative and arsenic more, there's charge transfer from gallium to arsenic. So all the filled states sit on the arsenic and all the empty states sit on gallium. And so it's as if we could put on goggles and look at the surface the way that a molecule or part of a molecule would. Think nucleophilicity and electrophilicity. And so that really opened up the chemical world to this microscope. And we've developed as a community and also in our laboratory, a whole slew of spectroscopic imaging capabilities that have better than atomic resolution like this. Now, one of the things that was a motivator for the talk today and the work today is the following. So in these extraordinary 2D materials you've been hearing about since the first one of these lectures, one of the difficulties is how do we contact them? And let's just take graphene as a nice example, because we're able to image it with our microscopes. We're able to do specific chemistries, as you'll see, to build or to grow it. And so in the case of graphene, the common ways to make contacts are either to evaporate metals on it, which ruin its extraordinary properties, or to oxidize it, breaking its conjugation, and then reduce it back a bit. And again, we've lost the key properties that we were after in the material. So my argument is we should be able to use more than a century of organic chemistry to learn to make carbon-carbon and carbon other atom bonds precisely like we'd like to have them. And then we should measure the molecular orbitals across those contacts with our spectroscopic imaging methods and ensure that we have optimized transport across them. That carries over to many other materials as well, such as in metal chalcogenides. We can swap in thiolates or selenolates or other molecules, as Taki Lee did in the passivation of molybdenum disulfide here. We think we can go further and we can build a molecular contact in that optimizes band alignment and transport across that interface. And I'll show you some progress, but no punchline there. Now, where my group came from is exploring the ultimate limits of miniaturization. And what we did was we looked at the smallest switches and motors in the world, synthetic, so we could go from quantum mechanics to mechanical engineering and experiment theory and simulation with these rigid molecules that we could understand, but we learned to isolate them into domain boundaries in self-sum monolayers. I'm just trying to give you a quick overview here, where we isolated them in a matrix. Christmas is coming, so I put the Love Actually scene here, where the Bill Nighy character got us to watch him sing and dance, much as our microscope would watch the function of the switch or motor isolated in a matrix. And we developed a whole series of tools to explore what was the contact conductance, what was the switching mechanism, and so forth. And it turned out in this case, for these molecules, the switching was actually a change in conductance. So just like semiconductors, contacts are everything. We developed tools to look underneath the surface so we could see where this buried bond was and thus measure the tilt. This is another cousin of the scanning tunneling microscope, and these measurements can be done simultaneously. We can measure the polarizability of the molecule, which, when the buried contact is conducting, includes the electrons of the substrate. And this was done with Terry's colleague, Mark Ratner, who celebrated a birthday earlier this week. Okay, now let's go on to the graphene nanoribbons and the work of Patrick Hahn, who started this work in a laboratory that we had together in Sendai, Japan at AIMR at Tohoku University. Patrick was particularly interested in chiral nanoribbons, the reason being that the armchair and zigzag graphene nanoribbons had been well studied and had interesting properties, and he hypothesized that there would be interesting spin properties of these chiral graphene nanoribbons. And so just to recap others' work, if one varies the width of an armchair nanoribbon, one varies the band gap. And graphene, as you know, is a semi-metal in its semi-infinite a planar state. And so this is a way to build a band gap into these materials. The zigzag nanoribbons have interesting spin properties at their edges. And then what Patrick was able to do, because we had developed this Ullmann coupling chemistry over the last 25 years in our group, was to design a precursor, much like Klaus Mühlen does at the Max Planck Institute, and know what the intermediates on the copper surface would be and how they would interact, such that when he raised the temperature and reacted them, we'd get these precise graphene nanoribbons. And that works. And the reason we use copper in this case is it's much more strongly interacting with the aromatics on the surface than are the silver and gold in its column of the periodic table. Okay. And so he was able to see these molecules before reaction as intermediates, and then upon raising the temperature and cooling again in the graphene nanoribbon that was formed. And indeed, he formed chiral graphene nanoribbons. According to the growth direction, they'd be left or right-handed. We don't have a color STM. He just color-coded these according to the growth direction, showing that they go left, right, left, right, left, right, like this. And then Nacho Pascal, a former postdoc in the group, now in San Sebastian at Nanogune, took the next step and worked on a vicinal surface in which the terraces were all in one direction and sufficiently narrow that he got one chirality everywhere on the surface. And we were able to, do the spectroscopies of these. We could do things like slide a halogen atom up to the edge of the graphene nanoribbon and quench the state and change basically what's a particle in a box to particles in two boxes by putting a node into those systems. There was a comment written on this paper which said, under different reaction conditions, we get a different product, so your mechanism must be wrong. And that we kind of said, okay, but at the same time, we wanted to take the comment seriously, so we reproduced those authors' conditions and showed that we did indeed get a different product, although we believe the mechanism was still correct. But what we noticed when we did that was, instead of getting the straight chiral graphene nanoribbons, we got these junctions. And junctions, to me, look like contacts. And so we said, well, here we have these contacts that we were trying to figure out how to make. Let's explore them spectroscopically. And so we did that. So in the straight graphene nanoribbon, for instance, we can show the continuity of the molecular orbital. And I'll point out that we can measure the phase of the molecular orbitals as well. And it's a much longer story, but those of you who know me know that I have PTSD about phase. And so I insist that we always measure the phase in these contacts. So for instance, this U-shaped nanoribbon looks in topographic measurements with the STM as if it's good. But when we look at the phase, we see there's a node at the contact. And so that is not what we want for a contact for these systems. And you know, all these stripes are indicative of nodes. And that tells me that we're, you know, that isn't what we wanted. And the idea then is to design a series of precursors that will give us a combinatorial array of contacts that we can then study to figure out which ones we want to target specifically when we, you know, go to town with the contacts we have. And we're able to explore all of them experimentally. And the plan is to lure theorists into studying these with us. In the meantime, we can also functionalize the sides of the graphene nanoribbons. This is work of Ling Bojing, a joint student I had with Kai Wu in Berlin, who showed that these sulfur functionalized graphene nanoribbons have band gaps that really only depend upon the length, and the sulfur can be in this cis or trans form, but that doesn't affect electronic properties. Other people have done some very beautiful work with side functionalization as well, particularly my colleagues here at UCLA, Yves Rubin and company, as well as our editor, Andrew Wee, at the National University of Singapore. And so this ability to do the precise functionalization and the precise assembly is just building and building, and really the precursor chemistry has been led by Klaus Mühlen and others to be able to let us assemble these precise graphene structures. The Berkeley group has done some really beautiful work in taking advantage of the idea that there are no nodes in the linear structures. I had thought, well, you can't make a device that's only linear because it just keeps going. But what they did in these nice demonstrations was show, for instance, for the armchair nanoribbons, by varying the width, you build a device in line by having the different band gaps in the center and on the outsides. And then they also did the side group functionalization, where using these zigzags and different functionalization on the sides, they were able to get different electronic properties across these segments. So I was very excited about that. Espresso, please. Okay, going back to the self-sum monolayers, those had all kinds of problems because the molecules out of which we assembled them were not rigid structurally. They could conformationally relax, they tilted, and so forth. And so a few years back, we came upon the idea that instead of using flexible chains, if we used rigid cages that stood upright on surfaces, most of the defects in those structures would go away by symmetry. And so we've been working with this upright cage molecules for some time now. Our favorites at the moment are these carboranes that are boron cages with 2 carbon atoms. And unlike what we teach in high school chemistry, that since the carbon atoms have 6 bonds here and behave like boron, they're electron deficient. One can make all of these isomers, one being our synthetic collaborators, not me. Here we were collaborating with Victor Belema, then at Sigma Aldrich, and now at Argonne. Now we work with our colleague Alex Spokojny at UCLA and Tomas Baza in Prague. And so by tuning the electronic properties of these molecules by design, by putting, for instance, the carbon atoms at the top of the molecule away from the surface, that makes the surface positively charged. By putting the carbon atoms on the side, that makes the surface nonpolar. And if we put the carbon atoms at the bottom, then that would make the surface negatively charged. And we're able to tune the surface charge just by choosing the molecules that we use, and you'll be able to figure out where we're going in terms of band alignment. We can see those effects at both the macroscopic scale and at the nanoscopic scale. And so Jay Kim in my group took that idea and he said, well, one of the problems with organic electronics is how do we get good alignment between the bands of the contact and the bands of the active material? And so people like Asef Martyr will put a polymer interlayer, they'll fluorinate it, and then that'll add negative charge. And that's the way that people have done the band alignment. But the problem with fluorinating a polymer is that's basically making that layer into something like Teflon and changing the wetting properties of the active layer. And if you change the amount of fluorine you put in, you'll change the wetting. And so Jay hypothesized that if we took two different carburenes and we mixed them on the surface, that we could then vary the surface charge essentially continuously, and we could get perfect band alignment in that way. And he did that using these two molecules. He was able to tune the surface potential over 1 electron volt, which is plenty, on both gold and silver surfaces. He was able to show that he didn't change the wetting properties and he didn't change the morphology of the active layer on top there. Okay. Now, for the last part of the talk, I wanted to talk about a spin. And so this is work really motivated by the discovery of Ron Naumann about the chirality-induced spin selectivity effect that one finds for chiral molecules. When electrons pass through a chiral film, there's the opposite spins don't have equal probability of transport, and I'll show you what I think is the most amazing example of that on the next slide. There are also ideas that the spin and chirality play important roles in biological processes, and my colleague and collaborator Clarissa Ayo at UCLA has been developing the questions to address whether that is something that's important in biology or not. At the same time, we would like to be able to use spins in and these molecular effects in quantum information and therefore be able to go up to room temperature or close to it instead of doing the kind of low temperature work that we're more used to seeing in the current quantum computers. So these effects have been quantified under many different conditions in different labs with very widely varying results. And we took this problem on much as we had earlier in the field of molecular electronics to try and see if we could have well-defined systems and thereby be able to see how big an effect it was, and also then to go further and see if we could optimize it. And to me, the experiment that really showed the effect most strongly was this one, in which one is doing water splitting, and a side reaction of water splitting is hydrogen peroxide production. And so that can only happen actually with a singlet. And if one produces a triplet for water splitting, one cannot make hydrogen peroxide. And so what Ron did with Bert Mayer was show that by controlling the spin coming out in these systems, they could turn on and off the side product. So it's really the first case where it was completely on and completely off. One can argue about what the quantitative effects were in many other cases, but this one I think really nailed it. That one can't argue with the result. And I've had two students in my group. Actually, Dominic Steamer defended his thesis earlier this week and is heading off to the Fritz Haber Institute. John Abendroth started this work in our group and is now at ETH. And what they've done is set up a series of experiments with carefully developed controls. So for instance, using the chemical patterning capability that I described in our, in the introduction, to be able to do something like 100,000 measurements at a time, in this case with patterned molecules and measuring fluorescence, that's a readout of what the spin effects are. We've done work with electrochemistry, with the synchrotrons at Berkeley, and Dominic lived up at LBL for a year and a half as an LBL graduate fellow in order to do these studies with a spin polarized LEAM, with the STM and so forth. So we've tried to look at as diverse array of systems as we possibly could to work out what are the effects, what are the parameters we can tune to optimize the spin. We've been able to take DNA, for instance, and intercalate metals and reverse its helicity, as Jackie Barden and Ted Chuang had done in another system across town here, and then look at proteins, look at synthetic molecules. And really our next step coming is due to an advance from Thomas Baza, who was able not only to synthesize chiral carboranes, but just very recently to separate them. So we're waiting for the end of the pandemic to be able to get those made in quantity. He's figured out how to do that, and then he will return to us and we'll look at the very well-behaved carborane sulfosome monolayers that are chiral on surfaces, so that we can, again, get in and do the comparisons between rigorous experiments and rigorous theory. I'll note that in the carboranes, we also have this ability to functionalize them. There was a big effort back in the 60s and 70s in which these were made in bulk, and all the chemistry was elaborated in two large groups, one in the Soviet Union and one in America. And so these are, scale up of these molecules is not a problem. And the functionalization selectively of them is also straightforward. Okay, so I wanted to make sure to leave plenty of time for discussion. And, you know, I've tried to give you a few, albeit atmospheric examples of the importance of contacts. Thinking from the bottom up, you can see how this idea that we can make atomically precise interfaces lets us control the chemical, physical, electronic, mechanical, optical, and spin properties at these interfaces. There's a tremendous amount to do here, and the nanoscience community is extremely well positioned to take advantage of these opportunities. We have, you know, both our speakers and many of you in the audience who have those connections between chemistry, physics, materials, and engineering that are going to let us put together the feedback loop to assemble interfaces, to measure these properties, to measure with atomic precision where the atoms are and ultimately where we want them to be, and then to work with our synthetic colleagues to build the precursors that let us assemble these interfaces over and over and over. And this, of course, developed because we had these new tools in nanoscience that gave us the eyes to look specifically at the interfaces, but not only that, to measure their functional properties. So we can measure, you know, tilt angles of molecules, contact conductance, and we have the ability to, you know, pattern those across surfaces to do those important control experiments. One of the things that held back the development of the cis effect, I would say, is that there were small numbers of measurements with very large error bars. And so another place where we can take a cue from biology is to build in as many control experiments as we can and to get the statistically significant data that doesn't come naturally to microscopic measurements. And so combining ideas from machine learning and sparsity and compressive sensing, as well as chemical patterning. I'm a little worried that I'm frozen here. Can someone hear me?
Yeah, Paul, I can still hear you. Yeah.
Okay, good. Yeah, my slides may be frozen, but we'll see what we can do here. So combining all these fields, and particularly the math and experimental design, then we have, you know, let's see if I can do it this way. Yeah, my slides are frozen, I'm afraid. But I will just, I think what I can do is leave this up. I tried to put everyone's name on every slide as I went along. The work that I described was largely paid for by NSF, DOE, the Keck Foundation, and a number of other foundations along the way. Really, what you see on the bottom right is what we'd like our microscope to look like, where we measure function, spectra, structures selectively and contextually. You know, and I'll make another argument for recruiting people into this area. There are tremendous opportunities And the effects of making better contacts are really significant, right? We lose, we basically put out a tremendous amount of heat from resistance in our devices. If we can optimize that, if we can optimize those contacts and reduce the heat, then we can make even bigger and more powerful devices. If we can learn to use spin, we can be much more efficient in the devices we make. If we can
Hi, Paul. We lost you. So I think due to maybe the internet connection, we lost Professor Wise temporary. So I would suggest we do the following. We will move on to the next presentation. Then when Paul's log back in again, we can do the Q&A and at the end. So let me next to welcome Professor Ashman Naik onto the podium. Let me do a quick introduction. He's an assistant professor in Department of Chemistry at the Indian Institute of Science, Education and Research. He received his PhD from the Indian Institute of Science in 2009 and then did a postdoc at the University of Chicago. He certainly has been starting his career for about 7 years now as a assistant professor, about 5 years now, sorry. He has done very nice work on novel semiconductor nanocrystals for optoelectronics application. He is the recipient of MRS India Medal and Young Scientist Platinum Jubilee Award from the National Academy of Science of India. And linking with Nanoletters, he's our early advisory board. With that, let me welcome Professor Naik to the podium.
Yeah, so can you hear me?
Yes.
Okay, fine. And I hope you can see my slides. Can you see the slides?
Yeah, slides fine.
Okay, great. Okay, so first of all, I thank Professor Kui, Professor Teriodome, and the rest of Nanoletters team for giving me an opportunity to share our work here. So today I'd like to emphasize some nanoscale phenomena, but in bulk materials. And to discuss such nanoscale phenomena, I'll take the example of optical properties of layered hybrid perovskites. So when we talk about nanoscale phenomena, we have seen in the previous slides very excellent interfaces that was shown by Professor Paul Weiss. And others kind of nanoscale phenomena, often we refer to the size effect. For example, I have taken this data from my PhD thesis. So these are cadmium selenide nanocrystals, about 5 nanometer in size. And optical data shows that there is an increase in band gap compared to the bulk cadmium selenide, which is the classic case of quantum confinement effect in a semiconductor nanocrystals. And then here, these are the cesium-lead halide nanocrystals. We see different colors because of the different halide ions that has been used. The sizes are about 10 nanometers in size. And we see the colloidal dispersion because of the surface chemistry of these nanocrystals. There are many other kinds of nanomaterials that includes like quantum oil structures or layered materials like graphene that was discussed in the previous presentation. So in all these cases, in all these systems, we see interesting electronic properties or surface related properties that changes with the change in the size of the crystal, and that's why we call them as a nanoscience. Now here what I'll try to say is that we can perhaps see some of this nanoscale phenomena even in bulk crystals, provided they have the right kind of crystal structures. So this is the three-dimensional perovskite structure, the famous ABX3 perovskite structure. So this is, for example, it is for cesium lead iodide perovskite structure. So you can see that these are the lead iodide layers which are connected in all 3 dimensions, and the voids that are created are occupied by the S-side cation, which is the cesium plus. Now, if the size of the void increases too much, something like when we get this kind of phenylethyl ammonium as a S-side cation, that time the inorganic octahedra gets separated from each other, and in between you see this kind of organic layers. So what you get is atomically thin 2-dimensional lead halide layers, and this gives you the quantum confinement. And then more importantly, you get the interfaces between the organic and inorganic layers, and these are nanoscale interfaces that are repeating over the 3-dimensional space. So you can see here, you get this entire crystal, for example, becomes the periodic arrangement of nanoscale interfaces. And that kind of nanoscale interfaces gives rise to interesting properties, and some of those I'll be discussing today. And throughout my talk, I'll be using this kind of layered materials that have this kind of generic structure, generic compositions, like we have the organic cation in the S side, then lead, or in 1 or 2 cases we'll have tin also, and the X is the halide ions that can be iodide, bromide, or chloride. So in this presentation, I'll be talking about bulk crystals. All of them are something like centimeter-sized crystals, and you can see the quantum confinement effect. Then we'll discuss about something called dielectric confinement, or some possibility of chiral optoelectronics, and also we'll be discussing about possibility of interactions between the inorganic layers. Now all these 3 comes because of the periodic nanoscale interactions that we have in the big single crystals. So before going to the optical properties and discussion, let me convince you that the material that I'm talking about, these are large single crystals. They have a lateral dimensions of about 1 centimeter and thickness of about 0.5 millimeter. You can take one of this single crystal, do all the optical properties and structural characterization on a single crystal. And so these are just showing that we have all the structural details. So these are single crystal XRD data at a different temperature. So we have complete understanding or complete knowledge of the structure of the material that we have, because we are studying single crystals. And the first observation is the quantum confinement effect, and I'm going back to one of the earlier figure that we discussed. So you get atomically thin inorganic layer, and if you look at the band offsets here, so if you look at the conduction band minimum of the inorganic layer and the organic layer's LUMO level, you'll see that the electron resides in this inorganic layer. Likewise, hole also reside in this inorganic layers. So you have the electron and hole residing in atomically thin layer, so that gives the strong quantum confinement effect. And then you get the layers of inorganic oil and organic barrier layer. So you get a repeating quantum oil kind of structure in these single crystals. And if you want to tune the extent of quantum confinement, you can do so by changing the thickness of the inorganic layer. So this is the generic formula. And if you change n, so if you go increase n, the thickness of the inorganic layer increases. And that's how you see the band gap decreases, because the quantum confinement effect decreases with increase in the thickness of the inorganic layers. So this kind of systems with n equal to 1 has been studied pretty extensively in 1980s, 90s by many groups, including the group of David Mitzi, and 2015-16 onwards, other groups, including the groups of Mercury Kanazitis, they have studied this kind of layers with n equal to 2, 3, and higher n values. So when the semiconductor absorbs light, we know that it creates electron in the conduction band and hole in the valence band. And this electron and hole then attract each other by a Coulomb force. And this Coulomb force is inversely proportional to the dielectric constant of the medium. Now, when I have this kind of layered perovskite, I have electron and hole residing in the inorganic layer because of the quantum confinement that we discussed in the previous slide. However, the lines of Coulomb forces extend not only in the inorganic layer, but also through the organic layers. So now you have a complex situation where the Coulomb force depends upon the dielectric constant of both the inorganic and organic layer. And in such a situation, to address a somewhat similar situation, Keldysh gave an equation long back. So this is the excitonic binding energy, which reflects the Coulomb force between electron and hole. So this excitonic binding energy for a 2D material here, you see a term here coming as a ratio of, so this excitonic binding energy increases as when the ratio of dielectric constant of the oil, which is nothing but the inorganic layer, and barrier, which is nothing but the organic layer here, increases. So this particular term increases the excitonic binding energy, and this particular term is what is responsible for something called dielectric confinement. To give an example of this, let me show here, you can see that this is the layered perovskite structure where we have changed the organic layer. The inorganic layer remained constant, and the organic layer is, for example, here it is phenylethyl ammonium. Then you get a dielectric constant, small dielectric constant for the barrier layer, that is 3. And for that, you get a very high excitonic binding energy. The excitonic binding energy is about 450 MeV. Now, this high excitonic binding energy is good for recombination of excitons and therefore properties like LEDs. However, if you change the organic layer to something like ethanol ammonium, then you get a higher dielectric constant for the barrier, and this reduces the excitonic binding energy to only about 50 MeV. So there's an order of magnitude change in the excitonic binding energy. We know that typically excitonic binding energy is an intrinsic property of a semiconductor, and here you can play over an order of magnitude in terms of excitonic binding energy just by changing the organic layer. And this gives a tremendous opportunity to look for different optical and optoelectronic properties. And that's how, and this is an example of interesting nanoscale dielectric engineering. For example, if you increase the thickness of this inorganic layer to something like 4-5 monolayer or 2-3 nanometer thick, then you will not see this kind of dielectric confinement effect. So it's a very much nanoscale phenomena, a size dependent one, and it comes in a bulk crystal. And we have got these numbers of excitonic binding energy, etc., from low energy, from low temperature photoluminescence data. And if you're interested more about the details, you can look at the paper here. So this dielectric confinement that I discussed here also get manifested in terms of halide ion composition. So if we keep other parameters same, and if we just change the halide ion composition, we'll know that in a 3-dimensional lead halide perovskite, as we go from iodide to bromide to chloride, the dielectric constant, so as you go from iodide to bromide to chloride, the excitonic binding energy binding energy increases. However, because of this dielectric confinement, when you come to layered perovskite, you see a reverse trend. When you go from chloride to bromide to iodide, the excitonic binding energy increases. So this reverse trend of halide dependence, 3D perovskite, the excitonic binding energy increases from iodide to chloride, but when you go to 2D perovskite, layered perovskite, it is the reverse trend. And this difference in the excitonic binding energy trend gives also difference in optical properties. So for example, you'll see that in a 3D layered perovskite, the excitonic binding energy here decreases from chloride to iodide, and therefore the lifetime, photoluminescence lifetime increases as you go from chloride to iodide, and reverses the trend when you go to 2D layered perovskite. So with this kind of after this kind of dielectric confinement effect, let me also just mention about the possibility of chiral optoelectronic properties. Now this is again a sort of an emerging directions in layered perovskite research in last 1-2 years, and we have not also done much of the work here. So I'll just briefly mention about the idea, and if you are interested to know more, you can go to this review article here. So the idea is that when you have this organic molecules, you can get the chirality very easily. And then when you have the inorganic semiconductor, there you know that the charge transport and electronic properties are pretty good. So if you can combine, because of this nanoscale interface, if you can combine this chirality and optoelectronic property of the chirality of the organic part and optoelectronic properties of the inorganic part, then there's a possibility that one could get like photodetectors, for example, that will detect circularly polarized light, or one can get LEDs out of this kind of layered materials that will emit circularly polarized light. And there are plenty of opportunity that opens up in this direction, which are some of this kind of chirality issues were discussed by Professor Paul Weiss in the previous talk. So this is sort of an emerging area that is coming out in last 1 and 2 years. So far, whatever we have discussed mainly about the properties that are coming due to the interaction between the inorganic and organic layers. However, there is also a possibility that there is an interaction between inorganic and both two inorganic layers, adjacent inorganic layers. And we came to this, we got motivated to work in this direction based on basically some experimental observation. So for example, these are the luminescence light, color of the luminescence that is coming out from this crystals of layered perovskite, and we see that under different measurement conditions there is a change in the colors. To understand this change in the colors, we did some spectroscopic measurement, and here what you can see is that these are the lead iodide layers, and this is butylamine. BA means butylamine lead iodide single crystals, and in these single crystals we cannot measure the absorbance because light cannot pass through the entire single crystal. So we measure the reflectance, and from reflectance we convert this data to absorbance, and you can see that it looks like there are two kind of absorption peaks. And very interestingly, for both the absorption peaks, you see two emission peaks that are coming out. And when you look at carefully, both emission peaks have their corresponding absorption. If we compare the FW full width, half maximum of the emission peaks, lifetime, etc., we come to a conclusion that both the emission peaks are excitonic emission. So this is somewhat unusual situation that from one single crystal, you are seeing two excitonic emission and two corresponding absorption. It looks like that as if the single crystal has two band gap, which cannot be possible. But importantly, all the layered perovskite material, when you make the single crystal of all this layered perovskite, we have made about 30 such composition by varying the acid cation, then lead versus tin and halides. And all of them have this generic feature that it shows two excitonic emission and absorption. If you want to see more of these examples, you can have a look at those papers that we published in last couple of years. So to understand this, the origin of this two excitonic emission, then we collaborated with Professor Arindam Choudhury from IIT Bombay, and they did specially resolved photoluminescence emission. So this is, for example, fluorescence microscopic image of one such crystal, piece of a crystal, and you can measure the absorption, you can measure the emission spectrum at different points, like at 1, 2, 3, 4. If I collect the absorption spectrum in these locations, and it is presented here, you'll see that for all the spots, we see two kind of emission peak. However, when you go to edges like spot 1 or 4, that is 1 or 4, in these edges, we see the intensity of the lower energy emission is higher and higher. This can be further probed by just having the specially resolved photoluminescence image for this small rectangular piece of the crystal. If you look at here, when we are at the edges, the emission intensity for the lower energy emission is much higher, and as we go towards the inside of the crystal at the interior, the emission intensity of the higher energy peak increases. So it looks like that the lower energy emission comes from the edges, but here you need to be careful, because when you look at the FESM images, you look at this is the FESM image of a piece of a single crystal, and you can see the typical signature of layered structure. So in this layered structure, even not only the crystal edges, but in the surface of the on the surface of the crystal also you see lots of edges. So therefore we termed this as a layer edges, and layer edges are there in addition to the crystal edges throughout the surface of the crystal. And because of that, throughout the surface of the crystal, we see some tiny contribution from the lower energy emission, which dominates at the crystal edges. So it looks like that since at the layer edges, the crystal structure is more flexible, probably the two inorganic layers come closer at the crystals, at the layer edges, and probably they interact to give rise to this new lower energy emission. To look at this, to verify this hypothesis, we also did some intercalation. So we have this layered perovskite structure, and to this we can intercalate various molecules, inorganic, organic. So here I'm taking the example of iodine intercalation. So when the iodine intercalates, you see that before the intercalation, this was the XRD pattern, and after the intercalation, you see that the interlayer distance increases, so XRD pattern shifts towards lower 2 theta values. And interestingly, this iodine can also come out. So it's a reversible process. So when iodine comes out, you see that the XRD pattern comes back to the original position. And interestingly, with this intercalation, so you see the black spectrum, that is before intercalation, we see the 2 peaks that we have discussed so far. But after intercalation with iodine, the low energy peak vanishes, and there is some tail, but it's significantly, it is gone, and you see a sort of a single emission after intercalation. So this suggests that probably there are some interaction between the inorganic layer, and the iodine intercalation breaks that interaction, and this layer, this emission that is coming from the interaction of inorganic layers vanishes after intercalation. Interestingly, as I told, that this iodine is this intercalation is a reversible process, and iodine comes out with time, and you see that with time the lower energy peaks reappears, and its intensity increases enormously when the iodine get de-intercalated. So the same thing here it is shown for another crystal. This is a phenylethylammonium tin iodide system with the different molecules. I'm not discussing this slide. And however, so this interaction hypothesis that we have, we can also verify it by changing the changing the chain length of the organic layer. So this is for C4 system, it's 4 carbon chain, and we can vary the carbon chain length to C16, and throughout this C4, C6, and we can vary in this from C4 to C16. And when we do so, we see that expectedly when we increase the chain length of the carbon chain, the interlayer distance increases, and that's what is reflected in the XRD data. Now, interestingly, what you see that for all this sample, the low energy emission remains fixed, rock steady. Sorry, the high energy emission remains rock steady, it doesn't change. It looks like that the high energy emission come from the isolated inorganic layer. And then as the chain length increases, carbon chain length increases, the interlayer distance increases. So the interaction between the inorganic layer decreases. And that's why you see this shift in the lower energy emission. This further supports our hypothesis that probably there is some kind of interaction between the inorganic layers. Now with this, I come to the conclusion slides. So today what I discussed is the properties of centimeter size crystals, but they have layered structure. And because of this layered structure, they have a periodically, there is a periodic arrangements of nanoscale interface, and this nanoscale interface gives rise to interesting properties at the nano level. So interesting aspect is that the entire crystal is the interface. So if you're looking for a property that are coming from interface like dielectric confinement or chiral optoelectronic, etc., they'll have a more prominent role in this kind of crystals that is full of nanoscale interfaces. And then we can do all this measurement from one single crystal. So we get a very clean measurement, doesn't have the uncertainties of size, shape, etc. And that will probably also help our theoretical colleagues to understand the structure-property relationship in a better way. So in today's example, I took the example of a layered hybrid perovskite, but there are many other such low-dimensional materials are there. For example, even the transition metal dichalcogenides in 1970s, there are examples of playing with intercalation of systems like tantalum sulfide and playing with the nanoscale interaction between the layers and getting the, in an attempt trying to improve the superconductivity parameters for those systems. Then there are one-dimensional systems. There again, there are lots of such nanoscale interface. So in a nutshell, what I'd like to say is that there is a big opportunity for this kind of bulk crystal with the lower dimensional crystal structure to play with the nanoscale interfaces in those systems. And getting inspired by Richard Feynman, I'll say that there is plenty of room at the interface of bulk crystals. And with this, I'd like to acknowledge the people who have done the work. So this is my group. So they have done the work, majority of work. And main contributions came from these three gentlemen that I mentioned earlier, and the funding comes from a government of India's funding agencies that include my institute, ISER Pune, and other funding agencies like ICRB and Department of Science and Technology. So with this, I thank you all for your kind attention.
Well, thank you, Ang Schumann, for the very interesting talk. Let me ask you first question. It's very interesting to see, considering this 2D layer perovskite, inorganic, organic. This is this interface right there. You could tune the property of certainly this quantum confinement right there already built in. There's also dielectric environment. So one question is these molecules and between the lead iodide, right? These molecules, they have their own bulk dielectric constant. Well, for molecular level, this dipole moment right there. So in the bulk level, it's kind of mixed, random. Now you have certain orientation of these molecules right there. How does this change the dielectric response if the molecules are packed in a different way versus random? And the dielectric response will be different. So through your measurement, looking at the optical properties and the exciton binding energy and so on, you can you actually back calculate the dielectric environment, based on the molecular orientation, the property binding energy you get. I'm trying to figure what I mean right here is maybe it's a unique system for us to learn about the interplay of molecular orientation, dielectric environment. So I want to see your comment on that.
Yes, so undoubtedly, I completely agree with your last comment that this is really interesting system to understand the kind of questions that you are addressing. But unfortunately, at this point, I don't see a direct tool. How can I see the change in the dielectric constant because of the orientation of the molecule? And at present, if I look at the literature, we are sort of relying on the computational results that are coming in that way. So I need to, so there is this problem of, because the dielectric measurement that I'll be doing, that will be looking at the entire crystal, both the inorganic and organic part. And getting the response from organic part alone when they're oriented in certain direction, as of now, it's still, I could not see that there are clear experimental technique to see that. So that's the situation. But I will be thinking on this direction, and I'm sure others will be also thinking on these directions, but let us see.
Yeah. Okay. So the second question is, these 2D perovskite to 2D layer right there. If you only consider each layer, well, it's all surface interface right there. And then it will be full of dangling bond with these organic molecules packing between the two layer of, inorganic layer, right? Would those dangling bond get passivated completely? Or there's still a lot of those dangling bond? But if there is a dangling bond, so what's the effect on the, for example, photoluminescence property? Yeah, how to think about this problem?
Yeah, so because of the structure of it, the layered structure, there is actually no dangling bond like MOS2, graphene, etc. These are layered structure, and you can have the 2D thing without dangling bond. This is the scenario here also. The lead iodide, all the lead and iodide bonds are saturated. They have made their covalent bonds. So there is no dangling bond as such. However, we see that with different kind of organic molecule that we put. So the interaction between the organic molecule and the inorganic part is essentially, you can see some kind of probably hydrogen bonding kind of interactions with the ammonium part of the organic ions, but there is no chemical bond, or there's no issues of dangling bond as such. But we see that with different organic molecules, there are difference in the response of photoluminescence, quantum yield, because there are some structural issues are also associated with different organic molecules and the dielectric confinement, as I mentioned earlier.
Yeah, I guess you are right, because lead iodide, iodine is group 7. So these 2D layers, just really no dangling bond. Moly sulfide also, it's saturated. But once you move on to the oxide, the things might be different. Yeah, I agree. So, Anshuman, with time consideration, I'd like to thank you for your talk. Let's move on to Terry's talk, but at the end, I'll bring everybody back for a panel discussion, and stay tuned, okay?
Yeah, thanks a lot.
Yeah. Our next speaker, Professor Terry Oldham. She's the chair and the Morrison Professor of Chemistry at Northwestern University. She obtained her bachelor degree at Stanford, PhD at Harvard. I was fortunate actually to have quite a bit of interaction in graduate school with Terry. We were sitting in the same office together. So throughout the years, I got to learn a lot about Terry. She is just an amazing person, very efficient, very effective. And that explained to her future career after graduation from Harvard, and so successful in Northwestern. Terry is very well known, similar as Paul, in the nanoscience community, everybody knows Terry. Recently, she stepped up to be the editor-in-chief of Nanoletters. Particular honor to have her to lead the whole journal. So before her leadership in Nanoletters, she was inaugurated associate editor for chemical science and founding executive editor for ACS Photonics. So you have seen Terry has been doing a lot of service to the whole community. Her research contribution is well known. She's recognized by, for example, she's the member of American Academy of Arts and Sciences. She's also a fellow of MRS. With that, I'll let Terry take over the podium.
Great, thanks, E. So I wanted to spend some of the time that we have today describing some of the history of nanoletters, partly so that it can inform in part where we're going in the future. And E had mentioned this earlier, but I'll just communicate it again, that this is the year and beginning of 2021 where we're celebrating 20 years of nanoletters. And so it's very exciting to see what has been accomplished to date and what is upcoming. So just a reminder of what I really like about Nanoletters is that it's a letters journal. So we're aiming for rapid dissemination. So it's a communication. So unlike our sister journal, ACS Nano, where the works are articles and complete work, ours is meant to be very rapid. It's just a short, important effort that wants to be communicated immediately. What we introduced this year is what's called a viewpoint, and I'll highlight some of them that have been contributed this year, where we're really looking for forward-looking pieces that says, okay, Nano's been here for so many years, where is it going in the next 20? What has been distinct also for Nanoletters is that we have an early career board who have been seminal in putting together these virtual issues and in general, being champions of the journal to younger communities. And also for the first time in the history of Nanoletters, we have an executive editor, which is E. Cui. And E in the early career board effectively brainstormed this idea during the middle of the pandemic to host a Nanoscience Global Lecture series. And so I think this series has been, it's been special. We're able to bring together established speakers, prominent scientists, as well as emerging ones. This is just an image of what was from last month with Andrew Geim, Omar Yagi, and Judy Cha, which was really nice to hear about the work even in the middle of these times. If you weren't already aware, I wanted to make sure that you were aware of this amazing associate editor team. I should mention that there were 5 new editors that started with me. Jen Dion, Chiwa Cheng, Lin Liu, Zhuamin Nan, and Vicky Colvin. And so all of the people on this slide are effectively leaders and directors of institutes. So they have a huge amount of expertise in trying to handle your manuscripts, and they also understand the pressures that are involved in these matters related to publishing. So I thought it was an interesting look to go back and evaluate what the top cited papers were over the past 20 years and looking forward to the future. And I think the evolution of the top cited work is quite interesting because it mimics a lot of the development that has happened in nanoscience to date. So if we started in 2001, the top highly cited paper from that year is related to cadmium sulfide, cadmium selenide quantum dots and their high photoluminescence. And then we have manuscript on the synthesis of single crystalline sulfur nanowires using soft tools, synthetic tools. There's the introduction of a silicon nanoscale silicon nanowire FET, field effect transistor. And then the first application, or one of the first applications of the use of these quantum dots related to biological activities. And can they be used for imaging, or are there potentially some deleterious effects? And then you'll notice that the interest in combining nano and biology continue, and it makes sense. And I'll talk about this a little bit just in some vignettes of my own work where the length scales are commensurate. And so there should be some synergistic, or at least some highly influential effects that can be done at these common length scales. So in 2005, the top cited paper was related to the use of gold nanoparticles to identify cancer cells. And then in 2006, it was related to how does the size and shape of gold nanoparticles affect cellular uptake. By 2007, the work focused on zinc oxide nanowires in terms of photodetectors. In 2008, the top cited work was related to graphene and the thermal properties. In 2009, the work focused on fabricating CVD graphene on a range of different types of substrates. And then in 2010 was the work on monolayer MOS2 related and their photoluminescence. So you can see a lot of the history of fundamental developments in the materials and then the application. Okay, so what about the second decade? So MOS2 rounded out the 2010, and again, MOS2 was as a transition metal dihydrogenide, was featured, but this time in platelet form with the photoluminescence observed there. In 2012 was the ability to make graphene quantum dots from carbon fibers and their use in cellular imaging. In 2013 and 2014, there's a move towards solar cells. So this is an inorganic, organic solar cell, and this is a different type of solar cell based on hybrid perovskites. And what's interesting about this paper is also it's a theory paper, really informed the design. By 2015, the top cited paper were these lead halide perovskite nanocrystals. And then you see a movement in 2016 and 2017 towards batteries. So lithium sulfide and these different polysulfide redox reactions, and then the electrodeposition of lithium on these metal substrates. And over the last 3 years, the work has been varied, which indicates that there's significant advances related to in all areas of nanoscience. And this is the ability to design cathodes for zinc ion batteries, different types of nanoscale constructs related to imaging and mouse models, and we're still in 2020, so this might be replaced or might hold its position in the next 5 years, but this is related to a theory guiding single atom catalysis, especially for lithium batteries. So you can see that there's a range of fundamental science that is driving advances, and I think it's very exciting. Okay, so that's 2 decades of just a slice of some of the work that's been highly cited and influential. And so then there was this idea on where are we going in the next 20 years? So over the course of the year, I invited leaders in different areas to brainstorm for us. So the viewpoints are intended to be just short articles that they can write as they're drinking their espresso, if you will, just want to get the good ideas out. And so we have ideas, related from lithium batteries to nano safety, to single molecules and molecular topology. So we are very fortunate to have these Nobel Prize winners say yes to nano. Louis Bruce had actually writing something different related to the rise of computation and nanoscience, Ned Seaman, DNA nanotechnology, and then Laura, who was a speaker on, I think, the first Global Nanoscience series, related to DNA technology and nanophotonics. New ways from Omar Yagi about becoming a reticular chemist, and then the importance of nanomedicine by Frank Caruso and Andre Nell, and then of course still the rise of nanophotonics and nano-optics, and then not finally, but bridges multiple dimensions is a piece by C.N.R. Rao talking about 0-dimensional and 2-dimensional materials. So if you haven't had a chance to read these, they're short. I would highly encourage you to do so. It might, I'm sure it will spark ideas for the future in the next 20 years of nanoscience. Okay, so in the 20 minutes that I have, I just wanted to tell you a couple of short stories related to trying to understand how single particles and their exquisite design combined in a multivalent way to proteins to really understand interactions at the single particle level. And this traditionally has not been an easy problem, but as I mentioned earlier, the biological length scale is commensurate with the nanoscale length scale, and so there is much to be learned in these types of systems. So the group that the students and postdocs that contributed to the work, they have all of these gold stars on their head, which is sort of symbolic, since I'll be talking about this structural unit, because I think there's many advantages to this shape. But here are a couple of examples of where nanoparticles and biological processes intersect length scale wise. So for example, in nanoparticle uptake mechanisms, you'll notice that there are a range of different length scales here, whether it's caveolar mediated endocytosis for 60 nanometer structures, clathrin for 120 nanometer structures, or these independent type of cellular uptake. They're all on the tens of nanometer length scales for the largest piece, but of course the smaller pieces are even less than that. So to be able to understand that and control those pieces, it's critically important. And another example of how nanoscale spacing dictates function is related to the growth of the collagen patterns. For example, gold nanodots with wildly different spacings. So depending on these types of spacings, it can result in different types of patterns that ultimately affect stem cell differentiation. So to be able to control these on the tens of nanometer scales is quite important. But there are some challenges. We need to be able to develop characterization tools and both probes. And moreover, we'd like to be able to observe these interactions in a dynamic way and not just a static way. And so we need to overcome some challenges related to diffraction. So we were interested in exploring a range of biological questions with this particular structure. Partly it's because nanoscale, the local nanoscale structure can give rise to macroscale chemical and physical properties. And moreover, this type of three-dimensional particle has different regions of curvature that can result locally in different properties. So by themselves, they show different physical properties, but as soon as the ligands are attached to the surface, the ligands are displayed in different ways. And so to be able to control ligand display will also affect different types of interactions with cells and other biological structures. So for example, in these positive curvature regions, they have high local optical fields because of the plasmonic effects, and because of the ligand presentation, they'll be all splayed out. In these neutral curvature regions, there's a high packing of ligands, which can stabilize molecules such as DNA or RNA that can be degraded quite easily by nucleases and enzymes. And in these negative curvature regions, these are these hydrophilic pockets. And there's been numerous studies related to attaching ligands of different functional groups and charges to control local pH. So by being able to use the structure of this particular system, there's a range of studies that can result. And so today I'll mostly talk about the use of the structure as a probe for both multivalent interactions as well as imaging. So when I say multivalent, I have in my mind where ligands are interacting multivalently, but also as we get to the structure, there's structural valency involved with this type of shape. And primarily today, I'm going to be focusing on how ligands, especially thiolated DNA or RNA, surround these types of structures. And so the ability to put DNA on a surface, a spherical surface, this was pioneered, or the application is also pioneered by Chad Merkin at Northwestern. And he found that there are several distinct advantages to organizing a three-dimensional presentation of nucleic acids. So there's improved stability against degradation. There seems to be higher cellular uptake, sometimes through scavenger receptors, sometimes through different methods. But also there's the premise that the functionality can be enhanced just based on the three-dimensional display. So the structure, the construct can act as a new unit and not just a ligand and a nanoparticle. However, there are numerous fundamental questions about how aspects of this construct are important in interactions. So how does the size and shape of the nanoparticle core dictate interactions? What happens if the ligand type is either targeting or non-targeting? What about the local shell composition and local density? So all of these are really important problems, but they're actually very difficult to do because they also involve care and a lot of analytical chemistry to get through these types of problems. Okay, so I want to tell you just two short stories related to these nanoconstructs interacting with proteins, and these are receptors in different cellular locations. We'll first talk about a drug molecule, which is a DNA aptamer. This is the ligand that will be on the surface, and then a biomarker that's a transmembrane protein and it's overexpressed. And so we'll be putting these DNA aptamer ligands onto the gold star as a probe to create these nanoscale constructs. And for this particular case, we're going to focus on HER2, which is a transmembrane receptor that's overexpressed on cancer cell surfaces, especially breast cancer. And the other system that I'll describe is related to this adjuvant, which is still based on a nucleic acid. But in this case, it's not targeting a surface receptor, but it's targeting receptors inside the endosome. And so the ability to look at these types of interactions at the single particle level are, I think, important. Okay, so let's start with the membrane first. So we're interested in these types of constructs. We didn't invent this construct. This one was published earlier by others who found that there was required to have a trimeric system to bind to HER2 and to produce a therapeutic effect. And the way that this process worked is that this aptamer would cross-link and sort the protein on the cell surface to the lysosome for degradation. This was the mechanism of action. And so we first compared the free aptamer to the aptamer that was attached to the gold nanostar. And you could see that there was significant decrease in cell viability or increased cell death when the aptamer was attached to the star compared to the free form, likely because the free form just degrades. And then we compared whether we actually do see a reduction in HER2 that's contributing to this cell death. This is a challenge with biology I found, is that you have to perform like 10 experiments to validate a single outcome. And so but they're all correlated, and I've learned to appreciate the complexity and all of that. And so you can see if we label the HER2 remaining on the cell membrane after incubation with the construct, you see it's indeed reduced, unlike the case where these cells are treated with the free aptamer. And then, of course, we needed to look at the actual protein content to quantify this effect, and not just looking at the decrease in fluorescence. And so you, in this Western blot, you can see that indeed there is significantly less of the HER2 left on the surface. Okay, so this is the system that we will work on, and we needed to understand the biology first. So we're interested in using differential interference contrast microscopy for this for these studies, partly because it's a non-phototoxic technique. It's a wide field imaging technique, and also you don't need labels. And so if we're able to look at intrinsic interactions between the ligands on the particle surface and then the structure and then the cells themselves, then we just eliminate some of the effects of bulky fluorophores. So the idea, I won't go through all the how this works, but you can see some of the ideas here. So depending upon the orientation of the metal particle, this is especially good for metal particles, you will result in a phase shift as the light is combined, it goes through and combined and interfered at the output. And so depending on the local orientation, you can, that will either result in a bright pixel or a dark pixel. So this is the contrast unit that we're interested in. And so we were able to, for example, to differentiate between two-dimensional and three-dimensional structures. So the two-dimensional structure looks like a rod, and it's just completely white, bright, or completely dark, depending upon relative orientation. And then similarly for the three-dimensional structure, you notice that there are these lobes there, partly because the structure is more complicated. But what's nice is, and we've just published this in ACS Central Science related to this three-dimensional structure and this type of two-dimensional contrast. So it's a really nice way to say, okay, in real time, we can determine what the local orientation is, which is hard to do because these particles are about 50 nanometers in size, so deep, so wavelength. So this is what the DIC image looks like of live cells. And so this is the bottom plane, the middle plane, and the top plane. And so you can see here also, as you just change the orientation over 180 degrees, you go from mostly bright, because this is the dominant mode, to dark to bright. And so we were interested in using this local probe, because metals scatter very brightly compared to, say, quantum dot probes. If we can develop a different type of biological assay just based on dynamics. So we focused on this targeting construct, which has the H aptamer, so it's targeting HER2 receptors, as well as this non-targeting construct. And the non-targeting construct has the same length of DNA and the same charge, but it's a scrambled sequence, so it does not bind to HER2. So if you're just, if you take a look at the both the area of span, translationally, how much of an area does it take on the surface, you can already see that it looks quite different if you have a targeting construct versus a non-targeting construct. And you can see how it's localized in different positions within this box for the targeting case, and then it's fairly localized in the non-targeting case. And I should also mention, which is quite interesting for these anisotropic particles, is that these targeting and non-targeting constructs, they have the same protein corona profile. So there's this idea that you have, once you put these into cells, the protein corona might deleteriously affect the exquisite nanoengineering of the particle. But it turns out that it's not the case for these anisotropic particles. It's different if you have symmetric particles, which we're finding out now. Okay, so what do these translation or rotational dynamics look like? We evaluated this for a number of different streams. You can see that the targeting particles have a range of different frequencies as they're rotating on the cell membrane, and they also, as I introduced earlier, span a large range of translational motion. But the non-targeting particles, not only did they not translate very much, but they spent a lot of their time just being fixed. They have very lazy rotational motions. And so just by looking at either the difference in the translation or the difference in rotation, you can identify whether the targeting particles are interacting with the cancer cells or not. So we looked at the different translational dynamics, and we can categorize them into standard, or we could fit them to standard diffusion related effects, where either the particles are stationary or they're simple diffusion, or directed diffusion, or even restricted diffusion. And so most of the most common type of motion is restricted, partly because there are a range of different contributors on the cell membrane. There's matrix involved. There are other types of proteins involved, and so it's trying to translate in this very complicated system. But what's interesting here is that if we look at the confinement length of these targeting particles for the non-targeting, this confinement length L is within the domain. It's similar to the domain sizes for HER2 diffusion. So the idea here is that the part of the reason the particles are translating so quickly is they want to find the receptor. And then once they find the receptor, they can bind, and then the kinetics change. And it changes sort of like this. So once the particle has found the HER2 receptor on the surface, it will be internalized. Let me just, okay, so we'll loop again. Okay, so this particle is flickering from bright to dark, partly because it's just rotating. And then you'll notice that there's some time here where it just stays bright, and then it starts translating away. So what this means is that once the particle has found the receptor, the particle stops moving. So you can tell this by the rotation. They're not rotating anymore, it just stays fixed. And then after about 10 seconds, then it's internalized, and then it translates in a directional way inside the cell. So this is pretty neat. It's one of the first times that we or the community has been able to understand the dynamics of single particle binding, very similar to what you might expect for some viral particle binding. So this is a different system, a different sample, same model system, where you can see here there's at these time points, there's no rotational dynamics. It just stays fixed. And then at a later time, about a minute later, because that's how long it took us to find the particle again, because it's now goes into the cell, then there is directed transport. Okay, so in the last 3 minutes, I just want to show this brief study that we've started to really understand nanoparticle endosome interactions. And so this is the cancer immunity cycle. And I think we're becoming more familiar now in the COVID area on how immunotherapy is actually quite important to treat viruses and disease, and so, or having your own body actually do it. So we are going to focus on this part, or which is called the adjuvant part, where we're looking to activate the immune system. And so the focus is on the use of these nucleic acids called CpGs, cytosine, phosphate, guanine motifs. So in mammalian DNA, these are methylated. If they're unmethylated, our immune system identifies them as pathogenic, and then these combine to TLR9 proteins inside of endosomes. And TLR9s are also involved in innate immune signaling. And then if TLR9 is activated, then cytokines are released that can stimulate an immune response. Okay, so in general, they're limited by their stability in the bloodstream, as well as poor cellular uptake. But as I introduced earlier, if you can put them on the nanoparticles, then we can stabilize the delivery. And so one of the first interesting findings was that you only need a small amount of CpG to immune activate the macrophages. You actually don't even need a shell of the CpG. So if these green bars just indicate the fraction of the active component for the oligonucleotide, you only need about 5%, which is pretty interesting. And then one thing to note is that these CpG constructs, they localize to the cellular components. They will localize to endosomes, as you can see here, for 2-hour incubation or 16-hour incubation. These big areas are the macrophages, but you can see that even the distribution of the spheres versus the stars for within the macrophages looks quite different. So we cannot understand this difference based on optical microscopy techniques, but we can evaluate this through some electron microscopy techniques. So the question we were interested in was whether the endosomal organization of CpG affected TLR9 activation. So this is what the TLR9 protein looks like, and we know it first binds to the nitrogen part, and then binds to the carbon end in a 2-to-2 stoichiometry. So this is what it looks like inside the endosome. And so we were wondering whether the effects of structural valency would, afforded by these nanoparticle scaffolds would affect the accumulation or the differences of these particles in endosomes. And so we found out that if we have these mixed curvature constructs, they tended to organize on the edge of the endosomes. But if you evaluated the effects of spheres, then these mostly accumulated within the middle. So this is quite interesting. These particles, in a comparative way, only have shapes that are different. The amount of CpG is the same. Let me skip this since we're running a little bit behind. And so what are the factors that control the formation? Well, clearly you need to have the targeting CpG bind to TLR9. If you have less CpG, then that's you increase the amount of the particles that are in the middle. Also, if you have non-targeting, then you mostly get these dense endosomes. And then if you block the TLR9, then again, you get these dense endosomes. So this indicates that in order to achieve these hollow endosomes, you need both specific interactions, the CpG, as well as strong multivalent binding. And of course, we want to correlate the distribution of these particles with the cytokine response. And so what we can see is that these constructs here that form hollow endosomes, they also show enhanced immunostimulatory activity. And these mixed curvature ones we can validate both on the APC, alkaline phosphatase secretion, as well as the cytokines that you see here. And then these constant curvature constructs, they just have the same or similar immunostimulatory activity at all densities. So what I like about this sort of fundamental system is that there's a spatial distribution of where the constructs end up, which results in a biological response. So I just want to summarize these two systems that I introduced. We're interacting with proteins. And we can use different translational and rotational dynamics to differentiate between targeting and non-targeting constructs. And then we can visualize the binding and anisotosис at the single particle level. And then for these immunotherapeutic applications, the organization of the nanoconstructs matters a lot. And through clever engineering, we can both control the structural and molecular valency, which I think are sort of new ideas and ways on how nanoparticles and their assemblies can affect biological outcomes. So I'll stop there and be happy to answer any questions.
Thank you, Terry. Well, it's really nice to summarize the past 2 decades of nanoletters. I think I get a lot out of it, seeing some of the past papers, but I'll leave that question to the panel discussion on that part. Let me ask you this, your own research program first. It's good to see, looks like in the last few years, you move ahead and really going into the nano and bio area a lot more. That's very, very exciting. So this nano construct idea, combining positive curvature, negative one, and also this flat region, I think is really, really cool. The question related to this basic construct, if I think about it, there's several questions. I think it would be great to get your insight. One is, looks like to get both translational and also rotational information, right? Particularly rotational. You want to have asymmetry.
Correct.
Nanostructure right there. Then asymmetry can be seen using a few ways. If it would be good to see your comment on the each of the spike coming out, their length, their arrangement, how many of them you should have. So, and any thoughts on those?
Well, this is partly why we like the star design. So if you control the length of the branch, you control the localized surface plasmon resonance. So we can image at the different wavelengths. So the DIC image is a broad wide field technique, but we usually have some sort of filter there that we can focus on the particle. So we'll usually have a filter right at the localized surface plasmon wavelength. And since the different branches can support different wavelengths, then you can image at the different wavelengths and then correlate that information together, which I think is pretty interesting. So it's similar to the beginnings of these super resolution techniques. At the end of the day, you get this really nice image, but there's a lot of processing that has to happen along the way. And so I think that's what the promise for these types of tools are. But it is possible. And also the structures that I showed you were made out with a single goods buffer. But there are ways to change out the goods buffer, and then you'll change the local orientation and presentation of the branches.
Yeah. So looking at, these the variety of choices possible within this nano construct, it's fascinating. Have you thought about combining this imaging, the spectrum, and the dynamics using machine learning, using artificial intelligence approach? Because the data set you're going to access is gigantic, right?
It's huge.
Yeah.
So the answer is yes. This is the paper we just published in ACS Central Science, where we developed deep learning technique to be able to predict what the three-dimensional orientation of the nanoparticles are, and it's a good model. I mean, it works well for rods. It works well for one orientation of the star. One branch, but the challenge is and I think it's actually promising because we will not be able to determine the 3D in the experiment, but the theory or the model can help us out with that. Yeah, so the model is actually quite robust, and I have a student, Jeng Chan, who had a minor in CS when he was an undergraduate. So that's been really great about being able to try to apply that to these sort of hard problems
Yeah, that's fantastic. So maybe one last question, Terry, for you. This spike coming out, does it go into the already the size range if there's interactions, biomolecules coming in, and the spike can get bent, the distance can change, then start to generate coupling, change the coupling between this spike?
Yeah, so they can't do it dynamically because it's an inorganic core, but you can make them with certain angles if we put them on the sphere. So if we start off with the sphere colloid and then we add spikes around like the last one, that's possible. But the structural valency is an important question because these are the length scales now. I mean, so for some protein interactions, you want they're at the 50 nanometer length scale, and you can do that easily with this type of architecture. And then I didn't show any high resolution TEM images, but the star tips, they narrow down to 2 to 3 nanometers radius of curvature, which is about the same size as a protein molecule. And so there are fundamental interactions and ways to probe, binding, even relative orientations on uptake that I think we can do with the system.
Okay, well, thank you, Terry. I think we start. Let me bring all the panelists back to stage. I have several questions I want to ask. I think all relate to all of you. Maybe Paul, I'll ask one question. You can take it first, right? In your talk, I think not only relate to yours and to the experiments, I think Terry can champion as well. And you describe this atomic precision control on materials. I really resonate with that. I think, the highest level of, making materials, you can have atomic precision control, arrange the atoms, creating the defects. You emphasize the interface, the surface, the chemical, physical, and electronic. And this is just fascinating. So, and just to brainstorming a little bit, this is a challenge. How do we really get there? We are making great progress. And in your talk, you show great examples right there. How do we get there? Yeah.
So I think there are ways to accelerate the process, right? We have the capability of making a combinatorial set of interfaces by starting with different precursors that are designed to give heterogeneity across the surface. One of the nice things about the microscopy that we do is everything we measure is homogeneous because we only measure one at a time. And so as we move around the surface, we're able to map, okay, this one has nodes, this one doesn't have nodes, or the equivalent. And so by doing the right experimental design up front, we're able to do many, many measurements and either go back to the same one or see if we can reproduce that chemistry and the reaction product is really what it is with a bunch of different precursors. And so there's you get to play both sides at the same time in these cases, just because of the way that we're able to do our measurements.
Yeah.
Makes it fun.
Yeah, that's great. And Shriman, do you also have comment on this?
Yeah, so this controlling this atomic size, atomic scale precision is, of course, it's very much challenging, and Paul has showed it wonderfully. And so for me now, I'm thinking it a slightly different way. So I'm also talking about nanoscale interface, but it's in a crystal. So for me, this atomic precision that I'm now looking for is where I'm not using microscopy, but using X-ray crystallography to look at it. And so it's both the cases, there are different advantages and disadvantages. And so both the things will coexist. But I think that at this point, since the field of nanoscience has become matured enough, we can see many of such crystal engineering aspects to see those interfaces. This will be addition to the microscopic atomic arrangement.
Yeah.
So maybe you could comment on that. I mean, you become more interested in this single atom catalysis, these types of studies, and I see a lot of single atom catalysis papers too, and they all look nice in the TEM, right? But I'm wondering if you have some comments on either the necessity or the distribution, you know, some of the fundamental things that are needed for that type of approach, maybe related to batteries or not, but just in general. I mean, that's ultimate precision, I guess.
Yeah, Terry, I think I really resonate with you. It's good single atom catalysis. I think it's a trigger as well, as part of the trigger to make people think about, well, down to single atom scale, and then what's the local environment and bonding affecting the property, and building it up from single to double to 3 to 4, and then how do you arrange that? Just build up more, and how does electronic structure change, and that evolving in the catalytic process, and many other things as well. I don't think we know how to do that yet. There is some examples of progress, but it's next 20 years on. I think nanoscience got to be very exciting. That's a one direction in thinking about it. This actually lead to the next question I want to ask.
Actually, before we go on, you know, I also really appreciate that side of catalysis, and I think the same strategy that we discussed is possible there. We can build up a set of varying, you know, onesies, twosies, threesies, and then learn to make the associations with what's the electronic structure we're looking for, and what's the relevant atomic structure that gives us that. And then by designing precursors again, either to stick into our catalyst or around which to grow the catalyst, we have an opportunity to make those targeted structures. And that's kind of been the dream of nanoscience, you know, for 30 years now. But I think the combination of synthesis tools and the machine learning and theory have all converged now. And the people on the panel even have an extra advantage, because as editors, we all have OCD. So we like everything just so, and it drives us a little more to push for those atomically precise structures and the kind of control that Terry and Anshuman showed. So,
yeah.
My thoughts.
So next question, for I think mainly for Paul and also Terry, and certainly Anshuman, feel free to chime in as well. Well, Terry, you were showing this 20 years of Nano Letter. I mean, I since Nano Letter started, I was a graduate student with Charlie Lieber. Right? I saw all the hot paper coming out. That's your most cited one is exactly right. This quantum dot, this nanowire, and then you start to see graphene, right? And then you start to see moly sulfide, and you see perovskite, and you see energy paper. You know, this sequence is roughly right with everything happening. What become the hottest paper? Well, Paul, for you first, did you see similar thing in ACS Nano? You know, the most cited paper is a Nano Letter is more or less similar.
Well, I'll start by saying every time I talk to Terry or see Terry speak, I learn something. So I also really appreciated that not only the historical perspective, but the way to look forward. So certainly in submissions, I would say we see fashions is probably the right way to put it. We see, you know, manuscripts kind of clumped together, but we're very much from the start trying to do what Terry described there, which is look forward and try and lay out, you know, what are the opportunities and the challenges. And so what we've done as editors is have a constant stream of communication, informally every day and formally every month, and under normal circumstances, meeting in person a couple of times a year, where all the discussions are focused on what's coming and what should we be accelerating through the platform that we have. So for instance, with the BRAIN initiative, right, we put together the technology roadmap, and you know, a bunch of us were working with the Office of Science Technology Policy at the same time to put that together as a program that would both bring public support to the field, but would also move nano into other areas where I think we have important roles to play. And so, one of the things I try to tell people about the journal is in most journals, you're not allowed to speculate, but we require it, that you're expected to say what the prospects of your work are. And I think that makes the papers more interesting and the journal more interesting. When we started, we had this idea that we'd be the public face of nanoscience and that we'd lay these things out, and we worked very hard to engage newspapers and regulators and decision makers to look at the field as a real opportunity for the world. And we try to judge ourselves on that, which is much harder to quantify as a metric. But if anyone has any suggestions about how, it would be most appreciated. And we also love hearing from our readers, and we have a Rising Star board following the lead of Nanoletters there. And so we try and survey people all the time about what do you think is coming? What are you looking forward to? Or what would you like to be able to do that you don't know how to do?
Paul, I like your response. You're fast. I asked you to look backward. You said, I'm going to look forward. That's great. So
I have a very poor memory, so it's easy for me.
So that's good, Paul. Terry, looking forward, and then from your perspective, and what's your thought about the journal? What about the topical area? Whatever you want to share with the whole audience.
Yeah, I think what was interesting in the beginning, just looking at the history, is it's fairly linear. You design a material and then you measure its property. And then once you know that well enough, then you can use it in some downstream application, batteries, devices, solar cells, drug alternatives. But I think, at least from my perspective on the future, some of the future of nanoscience is the continuous integration and synergistic interactions of fields. And so some of those initial works required, multiple fields, but I think really to moving the field forward, that's just the baseline. And so moving out of those fields that have been so important into others, like I think Paul mentioned, but also Louis Bruce wrote this, viewpoint is related to computation. So maybe or maybe not machine learning. I've talked to a lot of people about this, and I feel like, well, any of the machine learning that any of the chemists and materials people are doing is like old school baby machine learning. It's like the real machine people, that they're like, okay, that's not. So it's not really taking advantage of the cutting edge, and maybe that's necessary, right? You have to get some training and the low hanging fruit from other disciplines and applying it forward. But I think that will continue to be the case. I think this is the nice thing about nanoscience. So I don't. So Anshuman mentioned this word, and I don't want to pick on you for this, but I sort of have an allergic reaction to the word mature, partly because it assumes that everything is done, and I don't think that's the case. I think the problems now are more complicated than they ever have been, but we've had a falling off of the tools and the investments needed to really make the next big leap. Because what we're interested in, of course, is advancing new frontiers, but we have to promise things to lawmakers and the public. And I think we made some good steps, not falling into the GMO trap, but we made some poor steps on what could be delivered in the time frame, because there's always going to be a lag related to fundamental discoveries, integrating multiple disciplines, and then having something delivered as a product. This sort of some feedback that I got back when I was when I went to Washington. It seems like ages ago now. It was like 6 years ago. It wasn't under this current administration, and just talking to the senators about what they were interested in funding and why they liked nano, but they wish that there was just, a little bit more.
Yeah.
Maybe I can amplify two things Terry said, and that is, first, tools are incredibly important, and it's very hard to get investment in developing those tools. I'm hoping that by saying what it is we'll do with them, that we can help resolve that issue, but particularly in the US, outside of the national labs, where maybe people don't have the same exposure to the problems that we do at the broad universities where we work, it's a hard, sell to have the long-term investment that's needed. And the second is exactly what Terry said about public perception. If we don't get to the public, then the science fiction writers will first. And it's really important to get into the public's brain what it is we're trying to do for the world. And what we've heard through this series already in energy and sustainability and medicine, we have tremendous contributions to make. Other fields have established groups like the ACS or the APS or the MRS or AIMBE, and they're lobbying all the time in Washington. And other, in other countries equivalently, one of the piece of feedback we got is there's no one knocking on representatives' doors saying, what about nano? And we're in danger for not being vocal. And so it's going to be important for us as a field to figure out how to do that and to have a platform that has that sustained pressure and influence to say what it is we can do for the world.
Well, Paul and Terry, I encourage both of you, to step up to play leadership role on that front. So I think there will be a lot of people follow. Yeah.
Well, actually, there is. I was part of the panel. I was part of the National Academy's committee to evaluate the quadrennial review of the National Nanotechnology Initiative, and so that was quite interesting to be a part of. But that's just one study, and so now you have to take recommendations from things like that and just start preaching. Sometimes we get tired of that, but it's necessary, right? We're not used to just repeating ourselves over and over again. But I find that persistence is really important. So we'll continue to do that.
That's great. I know we have a lot we can discuss, but I need to respect everybody's time, including the huge audience, not in the Zoom, they are in different line viewing. So let me conclude today's event. So what a fantastic ending of this event, and draw the conclusion for Nanoscience Global Lecture for this year. Next year, we'll have a very exciting series coming up, so stay tuned, everybody. Starting from January, Paul certainly welcome to come into the view and look at what's happening in X-Human as well. So with that, let me conclude today's event, and thank you so much for your fantastic talk and sharing your insights about where nanoscience should go. Thank you.